Hello students, in my last class I have discussed about the cells in series as well as cells in parallel. What happens to the effective EMF when two cells are connected in series as well as parallel, and also to the internal resistance in series and parallel. In this class, let us learn the next topic, which is a very important one from this chapter, that is Kirchhoff's rules. Kirchhoff's rules. This is very important topic because using Kirchhoff's rules we can analyze any electrical circuits which are complicated. So we cannot apply Ohm's law everywhere, but the Kirchhoff's rules helps us to analyze the complicated electric circuits. Now there are two rules in Kirchhoff's rules. The first one is junction rule. Second one is loop rule. There are two rules, junction rule and loop rule. Junction rule is also regarded as Kirchhoff's current law, KCL, Kirchhoff's current law, and loop rule is also called KVL, Kirchhoff's voltage law. This is Kirchhoff's current law and this is Kirchhoff's voltage law. Now let us understand one by one. Let me take the first one, that is junction rule. Junction rule. In order to understand the junction rule, consider three resistors such that they are joined like this. There are three resistors here, or you can consider three conductors which are joined at this particular end, so that this is called as a node or a junction. This point is called as node or junction. Let us say that this is a resistor R1, this is R2 and this one is R3. Let us say that the current I1 is entering into the junction and current I2 is entering from this resistor to here, and at this junction let us say that the current I3 is leaving the junction. So you can look at the directions, the arrow marks here. From these two resistors or from these two conductors, the currents I1 and I2 are entering into the junction. But the same I3 is directed like this, because this is the direction of the current I3 which is leaving the junction. Now according to junction rule, Kirchhoff's junction rule, the algebraic sum of the currents entering the junction is equal to the algebraic sum of the currents leaving the junction. So from this particular diagram you can say that the currents entering are I1 and I2, therefore the sum of I1 plus I2, and that will be equal to I3, the current which is leaving the junction. So the sum of the currents entering the junction is equal to sum of the currents leaving the junction. Now if I make a change here, let me change this as the direction of I2 like this. I have marked the direction of I2 which is leaving the junction now. Now from this diagram, for this particular diagram, I1 is the current entering the junction and there are two currents, I2 and I3, which are leaving the junction. So for this one it becomes I1 is equal to I2 plus I3. See, if this is a junction, or sometimes we call this as a node also. So the currents entering the junction is equal to the sum of the currents leaving the junction. This is known as a junction rule. Let me write the statement of junction rule. algebraic sum of the currents entering the junction is equal to the algebraic sum of currents leaving the junction. Yes, this is the statement of junction rule. Algebraic sum of the currents entering the junction is equal to algebraic sum of the currents leaving the junction. Next, since the current flowing are uniform, no charge will be accumulated at the junction. No charge will be accumulated on this junction, so that Kirchhoff's junction rule signifies the conservation of charge. If the currents are entering into this junction, the sum of currents which are leaving the junction, that is equal to sum of the currents leaving the junction. So no charge will be accumulated here. So that this rule signifies the conservation of charge. So I will write it here. Kirchhoff's junction rule signifies law of conservation of charge. Law of conservation of charge. Yes, this signifies the law of conservation of charge. Next, we will move on to the next one, that is loop rule. Let us understand the second one, loop rule. Loop rule. First, before going to loop rule, if this is a resistor and the current is flowing from A to B, let us say that, or let us mark that current is flowing from A to B. So in this particular one, the product of current and resistance I into R is known as voltage, or you can say that as potential. I into R, V equals I into R. Since current flows from the positive potential to the negative potential, so here we should consider the product of I into R as negative, because this is a sign convention for applying the loop rule. When current is flowing from A to B and we are moving in the same direction, because if I multiply I into R in the same direction, then the product of current and resistance is taken as negative. Next, R, this is AB, and the direction of flow of current is taken in the same direction, I. So in a circuit, if I am coming from B to A, so if I am going from B to A, the current direction is reversed, so that the product of current and resistance V is equal to I into R. So this is considered as positive, because when we move from B to A, the direction of current is reverse of this one. So A to B is the direction of current, but we are moving from B to A. So in this case, the product of I into R is taken as positive. So V is equal to I into R is positive in this case. And next one is for a cell. For a cell, we know that current in a cell flows from negative to positive. This is the direction of current. We already know this. Now, if I say that this is AB, in a circuit, if I am moving from B to A, then the EMF of a cell is considered as positive, and for a same cell, AB. If I am moving from A to B, then EMF is considered as a negative one. EMF is negative. So this is the sign convention used in loop rule. So in resistor, when a current I is flowing through this resistor, when we are moving from A to B, the product of I into R is taken as negative. When I am moving from B to A in a circuit, the product of I into R is taken as positive. So in the same direction of current, IR product is negative. In the opposite direction of current, IR product is positive. Next, when we are moving from B to A in a cell, that is from negative to positive, EMF is considered as positive. When we are moving from A to B, that is from positive to negative, EMF is taken as negative. These are the sign conventions. So using this, let us understand a loop rule. Statement of loop rule is the algebraic sum of changes in potential once around the closed loop having cells and resistors is 0. The statement of loop rule is the algebraic sum of changes in potential once around the closed loop having cells and resistors is 0. The same statement is also written as, we can write one more statement for this, for loop rule. If I write one more statement, algebraic sum of EMFs and product of current and resistance in a closed loop is 0. This is another statement. We have two statements for loop rule, so both signifies the same meaning. The algebraic sum of the changes in potentials once around the closed loop containing cells and resistors is 0, or we can say this in otherwise, algebraic sum of EMFs and product of current and resistance in a closed loop is 0. How to understand this loop rule? For this, let me write a diagram. Let me consider a closed circuit having a resistors and a cell. And I will mark the corners as A, B, C, D, E and F. So we have a closed circuit now. Circuit is A, B, C, D, E, F, A. So from A, if I start from A, B, C, D, E, F, and again I will come back to A. So this is known as a closed circuit. A circuit is completed, or a loop. Or one more closed loop you can consider as B, C, D, E, B. This is one more closed loop. And if you consider this one, A, B, E, F, A. This is also a closed loop or a closed circuit. Now, in this closed circuit, let us mark the currents. Let us write the resistance first. I will write this resistor as R1 and this is R2 and I will mark this as R3. This is a cell. We know that in outer circuit current flows from positive to negative in a cell. Therefore, if this is the current entering into R1, the same current I1 comes here which is entering into this junction. Let us say that the current leaving this junction is I2 here and I3 here. The same current I1 is splitting into I2 and I3. Next, this current I2 comes here and I2 is entering into this junction, and current I3 which is entering into this junction like this. So I have marked the current and resistors, current and resistances. Now let us apply Kirchhoff's loop rule for one particular loop. I will consider a loop like this. Observe carefully. I will consider a loop like this: A, B, C, D, E, F, A. I am coming back to same one. A, B, C, D, E, F, A. So for a closed loop, A, B, C, D, E, F, A. Kirchhoff's loop rule says that algebraic sum of EMFs and product of current and resistance in a closed loop is 0. From A to B there are no resistors or cell, therefore I will move on to the next one. From B to C there are no resistors or no cells. Now from C to D, the current flowing through the resistor is I2. The current flowing through the resistor is I2. Now I will write the product of current and resistance. Product of current and resistance. I2 into R2. I2 into R2. The product of current into resistance is I2 R2. But from the sign convention, if I move along the same direction as the current flow, the product of I and R, current into resistance, is taken as negative, so that I2 R2, this product is considered as negative. We are moving in a direction of current, C to D. The direction of current is same from C to D, so that the product of current and resistance is taken as negative. So minus of I2 R2. Next I will come here. From D to E there are no resistors or no cells. Again from E to F, no cells or no resistors. But here we have a current I3 now. So when we are moving from F to A, we have current I3 and resistor R3. So if I multiply current and resistance, I3 R3, but the current is flowing from A to F, but I am moving from F to A, so that the product of current and resistance is considered as positive here. Therefore plus I3 R3. So when you move from this end to this end in a circuit, but the current is in opposite direction, so that the product of this current and resistance is taken as positive, plus I3 R3. Now to here we have a cell again, we have a cell here. So we are moving from positive potential to negative potential in a cell. Therefore this is considered as negative, and I will mark the EMF of this cell as E2 and EMF of this cell as E1. So from here to here we are moving from positive potential to negative potential. Therefore EMF is considered as negative. So minus of E2 equal to 0. This is how you can apply loop rule. Let me apply the same loop rule for another closed loop here. Let us consider this case: B, C, D, E, B. B, C, D, E, B. So let me apply for that particular loop: B, C, D, E, B. From B to C, no resistors. Now from C to D, we have a resistor R2 and current flowing is I2, and we are in the same direction as current. Therefore, the product of current and resistance is taken as negative. So, minus of I2 R2, minus of I2 R2. D to E, no resistors. Now, from E to B, we have a cell here, and we are moving from negative potential to positive potential, negative potential to positive potential. So in this case, EMF is considered as positive. Therefore, this is plus E1. This is plus E1. Next, here we have a resistor. Resistor is R1 and current which is flowing into is I1. So we are in the same direction as current. Therefore, product of current and resistance is taken as negative. So that this is minus I1 R1. This is equal to 0. And this is the loop rule applied for this particular loop. So, similarly, you can apply for A, B, E, F, A. A, B, E, F, A. So you can try this. A, B, E, F, A. So in a loop rule, since we have stated loop rule as the algebraic sum of the changes in potentials once around a circuit in a closed loop is equal to 0. This is signifying the law of conservation of energy. Law of conservation of energy. So in your examination, the question may be arised for one more question. What is the significance of loop rule, or what is the significance of junction rule? So we have already stated that the Kirchhoff's junction rule signifies the law of conservation of charge. Loop rule signifies the law of conservation of energy. Yes. So this is about loop rule and junction rule. Thank you.